Hello everyone. So today we are going to see the problem. Check completeness of a binary tree. So given the root of a binary tree, determine if it is a complete binary tree. In a complete binary tree, every level except possibly the last is completely filled and all the nodes in the last level are as far left as possible. It can have between 1 to 2 power h nodes inclusive at the last level h. So let's see what a complete binary tree means. It says that in a tree, all the levels should be completely filled. So if you look at this level is completely filled. Yes. This level, it is completely filled. This level is not completely filled. If it were completely filled, okay, then it would be a complete binary tree, no problem. But if it is not completely filled, that's still okay. But the thing is, all the nodes have to be as left as possible. Okay. Like these 4 5 6 these nodes lie to the left, right? This one is a null, so it's okay, it's a complete binary tree. Had it been the case that this this thing, if it would lie here, okay, if this node were here, this wouldn't be a complete binary tree because these nodes are not as left as possible, right? It's in the right, in the left we have a null, so all the nodes have to be as left as possible. Okay, so that's what a complete binary tree means. Now how are we going to solve it? The answer lies in our problem statement only. It says that every level should be completely filled. So we are talking about levels, right? We will have to see if each level is completely filled or not. Okay, we have to check level by level. So this gives us our answer. We will use a BFS, right? If we perform a BFS, what are we exactly going to do? See, how do we perform a BFS? A BFS traverses a tree in this fashion. Level left to right, isn't it? So the thing is, if we traverse from left to right, okay, and our tree is a complete one, then that means all the nodes will lie to the left, right? So when we traverse our list completely, we are we are always going to find unempty nodes, right? Node with values, not null nodes. But in case, let's say this is the case, okay, in such a case there would be a null, right? So when we traverse our tree, we are going to find a null here. Okay, we are going to find a null here. But the thing is, if we find a null here, there is not supposed to be any more nodes here, isn't it? In this side, it should be empty, right? In that case, if it were empty, this would be a complete tree. But after we found a null here, there still lies a node, an empty node, right? Node with a value. Then that means our tree is incomplete. So the thing is, if we do a BFS, okay, from left to right, as soon as we encounter a null, there shouldn't be any more nodes beyond that null. Our tree should finish there, right there, isn't it? But after that null, if we find another, if we find another node which is not empty, which is not null, then it's not a complete tree. Let's see how our BFS is going to work when it's an incomplete tree. Let's say this is our tree. Okay, we will have a boolean variable. Let's say seen or not seen. Okay, it's initially false. That okay, we haven't seen a null node, isn't it? Let's say this is our queue. Okay, so initially we put one here, the root node. Okay, now we see. Have we already seen a null node? No, we haven't seen. Okay, fine. Add its children 2 and 3. Okay, now we pop 2. We see. Have we already seen a null node? No, we haven't seen. Okay, add the children 4 and 5. Now we pop 3. Have we seen a null node before? No, we haven't seen. Add the children null and 6. Okay, now we pop 4. Have we seen a null node before? No, we haven't seen. Add its children null and null. Okay, we come to 5. Have we seen a null node before? No, we haven't seen. Right, we haven't seen. Add the children null, null and null. Okay, we come to null. Okay, finally we have seen a null node. Right, this is a null node. So we change it to true, that yes, we have seen a null node now. Okay, so there is no point in adding its children, right? So we come to 6 now. Okay, this is a non-empty node. Have we seen a null node before? Yes, we have seen a null node before. So the question is, if we have seen a null node before in our level, then where did you come from? You are not supposed to be here. You are supposed to be before our null, isn't it? If we have seen a null, then there is not supposed to be any non-empty node after this null. So that means our tree is not complete. Okay, so we return a false directly from here. Otherwise, let's say this was the case. Okay, there was no null here. Okay, so in that case we would pop the last node, isn't it? That okay, 6, we are at 6. Have we seen a null node before? No, we haven't seen. Okay, fine. Then we would add its children, null and null. Then after that we are all going to, all of them are null nodes, right? That means our tree is finally empty, right? There is no more nodes. So we saw that all the nodes that we have, that we traversed, okay, there was no null node in between them, isn't it? So the order that we traversed our tree, okay, we didn't encounter any null node, right? If there were any null node, that was after this, right, after this last node, isn't it? So that means that our tree is complete, isn't it? So in that case we will finally return a true. Now let's quickly write the code. So we need a queue to store our nodes, and we will add the root node into the queue. Queue.offer root, okay. And we need a boolean variable, let's say scene null equals to false, okay. So we haven't seen a null, right? So it's false initially. Now let's begin our BFS. While queue is not empty, pop the topmost node, denote current equals to queue.poll, right? Now if this node is a null, if this node is a null, we have seen a null finally. So we will update our seen null variable to true, that yes, we have finally saw a null node. Now our task is now to see that if there exists any more non-empty nodes after this null. If there is, then our tree is not a complete one, okay. So if our node is not empty but our seen null is already true, that means we have already seen a null, right? So in that case return false, okay, return a false. Otherwise add the children, q.offer current.left and q.offer current.right, okay. At the end return a true. So let me revise what we did here. If our current node is null, then that means we have seen a null node, okay. Otherwise if it is not a null node, then we will see that in the past have we seen a null node before it, right? If we have seen, then our tree is not a complete one. Otherwise we will just simply add our children to the queue, just the regular way we do our BFS, right? So that's it. And at the end, if we don't return a false from here, that means we never encountered a null node in between our non-empty nodes, right? So in that case we will return a true. Let's run it. Cool. Now what about the time and space? Clearly the time is a big O of n, and same the space is also a big O of n, right? Normal BFS, isn't it? N space for this queue, okay. So this is the solution. If you have any doubt, you can ask me in the comment section. And if you like this video, do hit the like button, share this video and subscribe to my channel, and I will see you in the next one. Bye bye.